So if you're going into teaching, this is called Blueberry software. It's $40 for an educator, and it's worth it because you can record everything that you're doing, and if any student misses something, if they're, that's where a lot of the high school teachers told me they spend their time trying to figure out what to do for all these random people. Because if you have 4 classes to teach or 5 classes to teach, and let's say one is gone from every single one of them, that's 5 people that are gone. And then you teach it every day, then you have a rolling 5 people every day. It starts to get confusing. So now you can just send them to the video and say, this is what you missed. And they, that way they're not coming to you. And I have had 0 people in my office ever since I started doing this. Not one, not even in pre-calculus, did anyone ever ask me for help in math. And I think the reason is either they find me frightening now and something's changed, or I think it's that they can rewind the thing, and it's a really key part of math, not seeing it once or recording it on in your notes and missing some of the things that were said. All those things combined made it so that I don't have it. And I used to have people in my office hours all the time. So they'd want me to go over problems again or do something again. And so it's not really that's doing a repetition or finding another way to explain it. It seems like the first way I explained it was fine, so far at least. And I've been doing this now for about 3 years. Not a single person in my office hours has ever asked me a question about math since that time, unless they were not in my class. They were asking me somebody else's class. So I think if you're teaching, it's a great thing. So what I wanted to show you today is a little bit more about Go, and I'm going to stop with Go, and I'm going to do next something called the Ducci problem. This is kind of how I got into combinatorial game theory, and it is so rich with abstract algebra. It's one of the most beautiful problems I've ever seen, and you'll really get to see how all of math comes together in this one really simple problem. But I want to give you some key deadlines first in between the Go and the Ducci problem. And and then ask you questions about how you would like the timeline to flow, because we're nearing the end now. So going back to the problem of Go, let's say we wanted to count. That's the problem. We want to count the number of legal moves on an m by n board. Well, one way you could do it is the way we have been doing it. It's called brute force. You just list all the 3 to the m times n possibilities, cross out all the illegal moves, and then count what's left. Well, we did it for some small ones. Maybe I would have had you in my office hours if I gave you a 5 by 5 board, because there's 400 billion configurations to check. So this is not feasible when the size of the board starts to grow. So whenever we find something's unfeasible, we try to find an alternate way. And when I say we, I'm talking about the mathematics community. So there's many beautiful open problems that are out there, especially in number theory, where you sometimes can check all possibilities. And combinatorics is that way too. You can count all possibilities. There's some amazing problems that are out there in combinatorics that are so interesting that I've shown them to students at a level that they're not even in pre-calc. And they get so interested in it that they start working on it instead of listening to the rest of the lecture. So that's how interesting those problems are. And you could have a computer sit there and try to brute force work out all possibilities, but mathematicians don't like that. They want what's called an elegant rigorous proof. So we're going to look for an elegant rigorous proof. I'm going to leave you with some documents after this so we can finish this. But the way to do this is to take those legal moves, make them into graphs, consider them as game graphs, and start counting things like the edges. So there's actually methods out there for counting paths. Graph theory is an old area of math. Euler, I think, was the first that developed the area of graph theory. So it's been around for some time, unlike combinatorial games, which has been, as you can see, around it's a very new area. But if you can recast your combinatorial game in graphs and count paths instead of counting things on the game itself, you have hope. So let's start back at the beginning. Recall at the beginning that we thought of this as a map where you're taking the board and rewriting that board into a grid. And with that grid, you can actually start labeling the locations on the grid with an XY coordinate system. Now we'll have to rotate this. Hi, Bill. That's Dr. Przinski. It's too big. Somebody asked me, random person asked me on the internet, who's Dr. Przinski and what's a Przinski proof? Like, He's actually just a professor at Montclair State, and we named it at the Brzezinski proof. It's not an official method. So recall that the way we did the labeling, 0, 0, the way that I showed you the labeling, is 0, 0 is the top left, and the x coordinates increase to the right, and the y coordinates increase downwards. So, for example, I just wanted to draw for you this one. See, that's why you don't want me to draw too much. Nothing looks straight. But this is supposedly a Go graph or a Go board with the labeling next to it. And this is a 3x4 board. So the way that they're going to do this is they're going to look at not the whole board, but partial. You can actually take the board and cut it up into pieces and ask what is going on in each one of those pieces. So really, if you remember playing the game Go, that's really what you ended up doing. You had these pockets. You were always looking for liberties where you can put your own stones. And you're always counting how many liberties that you had. Recall that last time I showed you how you actually can count the winner. So looking at the board in these little dissected pieces is pretty important. So this is the definition of a partial Go board. It's exactly what it sounds like. You just cut up the board into a little region and look at that little region as a piece. That's it. That's all it is, a partial board. It's exactly what it sounds like. Hi, Bill.
Hi.
Do you know what? We named your proof a Brzezinski proof. That's a proof that's completely done and everything's been checked. And I posted something on YouTube, and it was for the class. And some outsider looked at it and said, "Who's Brzezinski and what's a Brzezinski proof?" So you're famous.
Okay.
Have you guys had him?
I have a meeting with him for the credit.
Ask him to show you a Brzezinski proof. So what's a border state? A border state, or they just call it a state for short. If you sometimes they just call it a state for short, but sometimes they have to actually tell you because there's other words they use state in. It's a board of height m, and it's a partial column, and it's the color of those border points. So it's just the state that you have on the border of your partial board. That's the border state. That they call usually states. The configuration you're looking at is called the state. So you're just looking at what's happening at the borders, which is actually important, right? If you noticed when you play Go, what's happening on the borders kind of dictates how you can put things down. So the border is really important. And if you cut up your board and you're starting to look at partial positions of the board, it really matters what's going on at the border of those edges. And they have a definition here. The board is height m, the size of the partial columns, the color of the border points. It's all the information. It's like a little chart of all the information you would need to understand what's going on in your partial board. So it's a summary. So it's data. The number of connections you have with libertyless stones. So that's where you can place it. This is all the information for you to know what's in that partial board and what you can do in that partial board. So this is a laundry list, and I'm going to post this. So it's an inventory of the piece of your board. That's what all that list represents, and that's what they call the border state. That's the first 3 pages.